everyone. In the previous class, we discussed about the stress distribution all around the boundary of various non-circular openings such as elliptical, ovaloidal, square and rectangular shapes. And then I mentioned to you that how the stress distribution looks like under different in situ stress condition, that is uniaxial, biaxial and hydrostatic state of stresses. So, today based on those figures that I discussed in the previous class, we will discuss the design principles that can be derived from those figures. So, we will discuss case by case, that is for the 3 different stress conditions. We will take them separately and then we try to understand that where the maximum stress concentration is going to be, whether it is at the end of the horizontal axis or the vertical axis or at some other place. So, all those aspects we are going to discuss today. So, here I am considering the first state of stress, which was represented by m to be equal to 0, or we can say that it is the uniaxial state of stress. Please remember that m is equal to sigma h upon sigma v, and when I say that m is equal to 0, this means your sigma h value is equal to 0. So, here in the first column we have various opening shapes varying from circular to the rectangular, and in between we have elliptical, ovaloidal and the square shape. Now, for the elliptical shape we have considered 4 values of W naught by H naught. Please recall W naught be the width of the opening and H naught be the height of the opening. This is what is W naught, this is H naught. So, for the elliptical shape of the opening, we are considering 4 values of W naught by H naught, which are 0.25, 0.5, 2 and 4. Similarly, for ovaloidal and rectangular shape, we have the 4 values of W naught by H naught as 0.25, 0.5, 2 and 4. Then, as I mentioned to you in the previous class that we are going to focus on 3 values of the stress concentration, that is at the end of the horizontal axis, then at the end of the vertical axis and of course its maxima value. So, the same thing has been presented here for the circular case. These values are 3 at the end of horizontal axis, minus 1 at the end of vertical axis, and the maxima value was equal to 3. Likewise, for the elliptical opening, say I consider W naught by H naught to be equal to 2, then at the end of the horizontal axis the stress concentration factor is 5, at the end of the vertical axis it is minus 1 and the maxima value is 5. Similarly, for other shapes it is given. Now, from where these values are coming? You remember I showed you various figures in the previous class. So, all I have done is picked the numerical values at the end of horizontal axis, vertical axis and maximum value and compiled it in the form of this particular table for m equal to 0 value. Now, based upon these values, what we did here for elliptical, ovaloidal and rectangular shape where W naught by H naught is varying. So, corresponding to this I have the maxima value of the stress concentration. So, this is what that we have plotted here. So, on x axis it is width to height ratio, and in our case it was varying as 0.25, 0.5, 2 and 4, and on y axis it is the critical value of the stress concentration that we are taking as whatever is the maximum value of the stress concentration, that is what is the critical value. So, the one value that we obtain from that table which I showed you in the previous slide, plus we have the experimental values also with reference to the rectangular opening and ovaloidal opening. So, this circle legend is showing us the calculated data for ovaloidal shape, while this square shape legend is corresponding to experimental data with respect to rectangle, and cross is showing for the ovaloid, and this is what is the theoretical curve for ellipse. So, this theoretical curve I am getting from the value of the values which were there in the table in previous slide. So, what is the governing principle that we can deduce from here? That when you have width to height ratio greater than unity, this means this. So, towards this side of the figure, you have W naught by H naught greater than 1. Ovaloidal opening or rectangular openings with rounded corners, they will always give much smaller value of the critical compressive stress concentration factor. So, why is it so? You take a look here in this figure, see this is the theoretical curve for the ellipse, and if you just try to draw a smooth curve with respect to these experimental data, then you will see that you take any value of width to height ratio, let us say. Then corresponding to this, the stress concentration factor for ovaloid or rectangle shape is this, and for ellipse it is much larger than this particular value. So, therefore, we can say that when this W naught by H naught is greater than 1, it is the ovaloidal or the rectangular shape of the opening under uniaxial state of stress will give you lesser value of critical compressive stress concentration as compared to the elliptical shape of the opening having the same width to height ratio. So, that is what you need to keep in mind. Now, if we have the other side of the W naught by H naught, let us say this side it was greater than 1, but on this side this is W naught by H naught is less than 1. So, what happens here? That elliptical openings are giving us the smaller critical compressive stress concentration factor. So, take a look, you take any value and then you see this line is for ellipse. So, which is giving me the lesser value of the critical concentration factor as compared to the one that I will obtain for ovaloidal or the rectangular shape. So, depending upon width to height ratio, you can decide that which type or which shape of the opening is going to give you less value of the critical compressive stress concentration, and accordingly you can pick the appropriate shape of the opening. So, this is the first governing principle of design for the uniaxial state of stress. Now, coming to the second one. So, here I have put this table for your ready reference, is the same table that we had seen earlier. In this case, if the vertical applied stress is parallel to the height of the opening, then there will be the development of the critical tensile stress at the end of the vertical axis of the opening, and it will have almost the same order of the magnitude as that of the in situ vertical stress. Take a look here, at the end of the vertical axis is this column, and you can see that everywhere it is near about -1, either it is exactly -1 or maybe 0.7 or 0.8 or 0.9. So, this is what is the another governing principle for the design under uniaxial state of stress. if you recall, when we discussed about the circular tunnels, then I mentioned that it is the uniaxial state of stress which is critical, because at the crown portion of the tunnel there is going to be the occurrence of the tensile stresses, and therefore if the tensile strength of the material is less than the tensile stress which this opening is being subjected to, there is going to be the occurrence of the tension cracks, tensile cracks, and one needs to be careful as far as the provision of the support systems are concerned in the crown portion of the tunnel. So similar observation is seen here, that at the end of the vertical axis of the opening, you have the critical tensile stress, because here it is all -1, the stress concentration factors is all with a negative sign, and they have almost the same order of the magnitude as that of the in situ vertical stress. So please remember, this forms the second governing principle of design under uniaxial state of stress. I am emphasizing again that right now we are discussing corresponding to m equal to 0, which signifies the uniaxial state of stress. Then the critical compressive stress concentration, it increases as the radius of the curvature of the boundary of the opening reduces, and therefore the maximum or the critical compressive stress concentration need not to occur at the end of either major or the minor axis of the opening, but it will occur at a point on the boundary where you have the radius of curvature as the minimum. That is where the minimum radius of curvature is there, you will have the maximum stress concentration. And this is very striking, especially in case of the square or the rectangular openings with rounded corners. Although it is also evident from this table, but then I will have a figure also with respect to the square opening here. This is the square opening where you have W naught by H naught to be equal to 1. And the sides of the squares, they are parallel to the axes, x axis and y axis, as you can see from here. Now you see, at the ends of the vertical and the horizontal axis, the radius of curvature is almost infinite, but in this zone where it is minimum, so you see that the maximum stress concentration is occurring in this zone, that is in this case m equal to 1 it is here, for m equal to 1 by 3 it is here, and for m equal to 0 it is here. So these are the locations, these correspond to approximately wherever you have the least radius of curvature, which happens to be in this zone. So this makes the next governing principle for design under uniaxial state of stress. Then the tangential stress concentration on the extension of horizontal axis. Take a note, it is on the extension of the horizontal axis through any opening of any shape is maximum at the boundary, and it reduces rapidly with its distance from the boundary. Then another thing which you have to note here, that more the boundary stress concentration factor and more rapid is going to be the reduction of this stress concentration with distance from the boundary. Let us take this figure and try to understand this. So what I said was that extension of the horizontal axis. So I extend, here is the end, so I extend this horizontal axis, and you see that here near in this region only you are getting the maximum value. You take any figure, okay, and approximately on those zone you will have the maximum value, and you see that as you move away from this horizontal boundary, see how the stress concentration factor is reducing. Okay, so you can see that it is almost true in all these situations of any shape of the opening having any value of W naught upon H naught. Okay. Now another aspect which was there, that more the stress concentration and rapid is going to be the reduction with the distance from the boundary. So take a look for example at this figure. Here you see corresponding to m equal to 1, this is the maximum stress concentration factor. And you see when you go away from the boundary of the opening, so you see that this m is equal to 1, see how it is going here. The reduction is so rapid here. Okay. So similar is the situation which is seen, you can see here m equal to 1, maximum stress concentration, but the reduction is rapid when you had more stress concentration when you move away from the boundary. So this makes the next governing principle of the design under uniaxial state of stress, that at the extension of the horizontal axis you are going to have the maximum stress concentration factor which reduces with the distance from the boundary. Then larger the stress concentration factor, rapid is the reduction of the stress concentration factor. Now coming to the next state of stress, that is biaxial. And when I say biaxial, that means that you have the stresses, applied stresses in horizontal as well as in the vertical direction. So here we took a typical value of m as 1 by 3, which is equal to sigma h upon sigma v, and this gives me sigma h to be equal to 1 by 3 sigma v. So it is not that this is the only biaxial state of stress. You can have sigma h to be equal to say half of sigma v, or maybe 1/4 of sigma v, or let us say any other factor. Here typically I am considering this m to be equal to 1 by 3, and I am calling this as a biaxial state of stress. So like we had in the uniaxial state of stress condition, here also we had the stress distribution plots which I showed you in the previous class. So from those plots only we picked the numerical values at the end of the horizontal axis, at the end of vertical axis, and the maxima value all at the boundary of the opening, and we have presented it here in a form of the table. So for the circular opening shape, at the end of the horizontal axis, the value of the stress concentration factor was found to be 2.67. At the end of the vertical axis, it was 0, and the maxima value was also 2.67. For elliptical, ovaloidal and rectangular shapes, we considered 4 values of W naught by H naught, which were 0.25, 0.5, 2 and 4. And accordingly, we had the respective values of the stress concentration factor at the end of horizontal axis, at the end of vertical axis, and the maximum value. Now come to the square opening. There you can see that the maximum value is occurring at the corner. Similarly here in case of the rectangular one, this maximum value is occurring at the corner. You remember I mentioned to you that the maximum value will be there wherever you have the minimum radius of curvature. And therefore, we can derive some of the governing principles with respect to the biaxial state of stress when m assumes a value of 1 by 3. So from that table that I showed you in the previous slide, again here as we did in case of the uniaxial state of stress, we try to plot the value of the critical compressive stress concentration with reference to width to height ratio here. So there are 3 plots as you can see. One is for ellipse, this is for rectangle, and this dotted one is for ovaloidal shape of the opening. So some of the points that you are seeing as a rectangular legend. These are the experimental data, and remaining this round or circular legend is the calculated data. So, in this case you take a look at this figure and then read the text which is given here, and then try to understand what is the governing principle of design that we can have from here. An elliptical opening with its major axis parallel to the vertical applied stress will develop smaller critical stress concentration. Now, you see, when I say an elliptical opening with its major axis parallel to the vertical applied stress, this will give you the idea about the ratio of W naught upon H naught. Now, for a given stress field, if this W naught by H naught ratio equals SV by SH, then the critical stress at all the points on the boundary, they are compressive, constant and a minimum, and hence the elliptical opening with the proper ratio of major to minor axis becomes the ideal opening for any stress field other than the uniaxial one. So, you see here that if I have W naught by H naught like this, where you have the major axis parallel to the vertical applied stress, this will always develop the low value of the critical compressive stress concentration in this zone. Then when you have W naught by H naught to be greater than 1, okay. So, this is what is the zone where W naught upon H naught is greater than 1. It will be the ovaloidal shape, you see this one, which will give you the least value of the stress concentration factor. So, when we have this type of the size of the opening, then it is better to go for the ovaloidal shape, because it gives you the minimum value of the critical compressive stress concentration factor as compared to the opening of any other shape. Now, the tensile stresses at the end of the vertical axis of all the opening in the uniaxial stress field will reduce, and it becomes compressive when you increase this mobilization factor m from 0 to 1 by 3. For W naught by H naught less than or equal to 1, this transition from tension to compression, it occurs at 1 by 3 value of m. So, you see that both the tables I have pasted here, this corresponds to m equal to 0, this corresponds to m equal to 1 by 3. So, take a look at the end of the vertical axis here, and this is here. So, here we saw that these all values are negative. However, in this case most of these values now are positive, except for the elliptical case here and the ovaloidal case here, square, and the rectangular shape here. So, most of the values, they are transitioning from the negative to compressive stresses. So, this is what is the next principle of design for the biaxial state of stress, having the value of m as 1 by 3. Then we come to the next state of stress, which is the hydrostatic state of stress, that is m equal to sigma h upon sigma v, which is equal to 1. So, this gives me that sigma h is equal to sigma v. Now, in this case again we have developed similar table with respect to various opening shape and different values of this width to height ratio of the opening, which is represented by W naught by H naught. So, we have taken as usual in the earlier cases also, here we have taken 4 values of W naught by H naught, that is 0.25, 0.5, 2 and 4, and then we have obtained these values from the figures that I showed you in the previous class corresponding to hydrostatic state of stress, and have compiled all these values at the end of horizontal axis, at the end of vertical axis, and also the maximum value. Now, like we did in case of the uniaxial and biaxial state of stress, here also we are going to plot these values with reference to W naught by H naught, and let us try to obtain some of the design principles. So, here on the x axis you have width to height ratio, which is W naught by H naught, that theoretically we have varied it from 0.25 to 4, and then on y axis we have the critical compressive stress condition. So, in this case you can see that irrespective of the value of W naught by H naught ratio, the most preferred shape of the opening is ovaloid. So, you see that this plot is for the ovaloid shape, and whatever is the value of W naught by H naught, this will always give me the least value of critical compressive stress concentration. So, this will always be the most preferred shape of the opening as compared to ellipse and the rectangular opening. However, you see, take a look here at when W naught by H naught is equal to 1. So, here you see you have the ovaloidal shape, you have the ellipse, and when this W naught by H naught is equal to 1, this is also corresponds to the circular opening. This will also give the least value of the critical compressive stress concentration. Then the hydrostatic state of stress will always give, or it will always result in an all around compressive stress situation all around the periphery of the opening. As it is evident from this table, you see not even a single value of the stress concentration factor is negative. So, this means that applied stresses we consider to be compressive, and since these all values are positive, that means that the stress which are getting generated because of this applied stresses, they are also compressive in nature. So, we can say that the hydrostatic state of stress, there will not be the occurrence of any tensile stresses around the periphery of the opening. So, one does not need to bother about the tensile strength of the material. Now, because there is no development of the tensile stresses, the stability of the underground opening will improve even in case of the rocks for which the tensile strength is very small. As I mentioned that you really do not need to bother about the tensile strength of the material. So, the design equations are going to be this sigma T tensile multiplied by the factor of safety will be less than or equal to Qt, which is the tensile strength of the rock. Then sigma T compressive multiplied by factor of safety should be less than or equal to Q sub C, which is the compressive strength of the rock. So, these are going to be the design equations. So, this is how for different state of stress, whether it is uniaxial, biaxial or hydrostatic state of stress, we can find out the stress distribution and therefore derive some governing principles for design for various shapes of the opening such as elliptical, ovaloidal, square and rectangular shapes. So, this was all about the stress distribution all around the boundary of the non-circular opening. Now, till now we have considered only the single opening, but then you can have the situation where you have to go for more than one opening. So, in the next class we will take up the study which are related to the multiple openings, and then we will see that how these stress concentration factors they vary when you have the multiple openings, or what is the influence of one additional opening onto the stresses which are there in case of the single opening. Thank you very much.